Hello, my name is Miguel Torres. I am part of OSBA's class for fluid mechanics in summer of 2025, and this will be project 3 of this semester. Project 3, there are 3 parts. I'm going to do one video for each part, and so yeah. For starters, we will start with the inviscous flow. Do keep in mind in this first video I will do the mesh, and the same mesh will be reused in the 2 different cases. So that might. So to start with, we will put a mesh in here, and then we will go fluent, not fluent with meshing, just fluent, and connect that with the mesh. There you go. This setting it up like this, we could also set up the other cases, just sharing it as well. But for now, we're going to start with the inviscous flow. Inviscous. And there you go. All right. Be sure to set this as 2D and then open it. Okay. Takes a little while to open it up, but we're there. We're going to do, for this simulation, we will be doing a flow over a cylinder. But since this is 2D, is you're just going to have a circle represented in the flow. So make sure you're on sketch, you're on the plane view, and now we're going to insert our circle. Dimension this. In the assignment, it is 1 meter in diameter. Then we put our domain in here. I'm going to do, let's see, I'm going to try doing 15 meters. We're going to see how that works. 15 meters, 15 meters, 7.5 meters. Looks good. There's something is lacking. I'm gonna go 20 meters on this one, just so we could capture more of the wake passing the cylinder. to press D or press the body mode, 3D mode. Once you're here, Control G, select the edge, Control G, and name it. Go. That's done. Close it. Now we're on the mesh. How to plug in the charger. Alright. Okay. Alright. We have our name selections in here. Also, it is known that you could design this domain in Design Modeler instead of Discovery, and you could do the name selections in here in Mesh or in Design Modeler if you want. But alright, now before we generate the mesh, we gotta set some refinements. So what I'm gonna do is go here, select the cylinder wall, and in here I'm gonna put number of divisions to 250. The behavior will be hard, and always good to rename these things. Now I'm gonna insert the method and put this as triangles. And finally, we're gonna click on the face. We're gonna do an inflation. This will capture the boundary layer. So boundary will be the cylinder. First layer thickness 0.02. Close that. Maximum number of layers 100 and 2.5 for growth rate. There we go. Now once we go to the mesh, element size, we're going to go 0.15. Generate mesh. Okay, the mesh looks alright. It's pretty clean. It looks good. There you go. Alright, we could close this right now and update the mesh. Okay, I'm gonna go double precision and 6 cores. There we go. 6 cores because it's my laptop, and double precision because, well, It's double precision, so it would be more accurate. Let's start. Well, not sure about the double precision. To be honest, I always use it. Um, if anyone does know about the double precision, what it really does, please let me know. But that's just what I always use, and it just always works. So, now you see got an error. In my previous videos, I also had this error a lot of times, and that's because of the cell zone condition. You see this whole surface as a solid, and there's no fluid to simulate. That's obviously wrong, so change it back to fluid and apply. Close it, and well, we clear all the errors. There you go. Now, based on what we're simulating, well, first of all, leave this as default, steady, pressure-based, and absolute. This could just be left alone. In viscous, we're gonna go in viscous. That's the model we're gonna use to solve this. It's just an in viscous simulation, so there's no viscosity. So close that. Close that. Materials. I leave as default. Just the air, because it's just air. I think it's a little bit more realistic if we leave it like this. So just leave it like that. Fluid. Yep, just leave this alone. It's good. And then boundary conditions. Now in the assignment, we are, for the in viscous case, we are given a velocity of 5, and everything else will be left alone. This is good. The outlet is good. For the outlet, I would try preventing reverse flow. No, let's leave it as is and see how it really does. I don't think it really should need prevent reverse flow. Tried it before and it didn't really need it. Now for the in viscous case to work, we will need to mess with the solution method. And here we're going to go simple instead of coupled. And then in pressure, we're going to go presto. And there you go. If you're wondering what this means, simple means it will just use simple equations. Coupled means the equations that they use to solve this will be coupled to each other. Of course, coupled might be more accurate, but it will be a lot more difficult to calculate in some cases. And if you were to use coupled in this simulation, you may get a weird behavior where you're gonna have like a low pressure area in here and on the cylinder, but then a high pressure area in the middle, and it would just behave strangely and it would just lead to an inaccurate result. So that's why we will use simple instead. So it will give it much more easier calculations to calculate this more properly. And report definitions, new, force support, drag coefficient, cylinder, name it. And I like to print it to console so you can see it down here. Okay. Monitors, I'll go 1E -5. There we go. And then for initialization, you're gonna probably need a little bit more iterations. I'll just go 20. And then wait, before we do that, we gotta change our reference values to compute from inlet. If we don't, then our coefficient of drag will be wrong. So And make sure it's compute from inlet. And then now we initialize. All right, that's done. I'm gonna put number of iterations as 1,000, though cut short because of that convergence criteria we set. And yeah, and now we are ready to actually calculate the result. Okay, the calculation is complete. Residuals went below 1e -6. That's good. So now we could actually get our data. If we want to get our coefficient of drag, go to report, and then compute. And we see our coefficient of drag is pretty much near 0. I believe that's to be expected in an inviscous flow. So now we're going to try getting our pressure and velocity contours. First, let's start with pressure. contour, and there we go. Looks good. No weird behaviors going on. It's alright. And let's do the same for velocity. Yep, looks good. And then we will also need to graph our coefficient of pressure and and the velocity along the surface of the cylinder. So in plots, go here, click new, and let's in this pressure coefficient along the cylinder. Um, when in our report, we will click write to file, so write it. For now, I'll just try plotting it. So yeah, plot, and there you go. That is to be expected, and it matches the contour that we see. You see how pressure coefficient is just 1, and as you go across, you get a negative, and it goes back to 1. Basically just matches our contour here, 1, and then as you go up, it goes negative, and then goes back to 1. Well, I mean, yeah, it pretty much matches. So it looks good. Next, we got to do velocity along the surface. Here, velocity, magnitude, and then on the cylinder. And yeah, that's also to be expected, just a circle. You start at 0, that's our stagnation point. And then as we go along, since the pressure is negative, we get a higher velocity. And then as we go back to closer to a positive pressure, then we hit another stagnation point right here. So looks good. And yeah, that's pretty much a simulation. Of course, you could run a vector, velocity vector on it if you want, path lines. We also need to run streamlines on this one, so let's do streamline, velocity, streamline, a stream function, velocity, stream function, remove filled, and then click draw mesh, draw cylinder, and then plot it. Looks good. Goes to play with all this, but it's alright. Yeah. And that is in the Inviscid part of the simulation done. The Inviscid case is finished. And yeah, there you go. Next, we will do the laminar simulation.